Hey, this is Steven from LegitTechTutorials, and welcome to my first video on my new series on my LegitTechTutorials channel. And what it is on this series we're going to be doing product development. So we're going to do an actual full-blown product that is going to be drawn out in tutorials. So this particular product that we're going to do in this first development series, product development series, is called the multi-shooter dimensional control and spooler. So a multi-shooter is a product I developed under the business name of the Green Engineers, and what it is it's a 3D printer filament maker. So what happens is you put in plastic at the top and it melts the plastic down to a wire, otherwise known as filament. And then this wire is used on a 3D printer, an FFF or an FDM printer that basically melts the plastic in layers to create a full 3D printed part. So the filament maker makes the wire or the material that is used in the 3D printer. So now the standard version of the multi-shooter just takes, just extrudes the filament and then it just spirals on the floor. So now what we're going to develop is an expansion module, two expansion modules to the multi-shooter. And what it does is one part called the dimensional control will measure the diameter of the filament to make sure that the filament is the correct diameter for the 3D printer. Because in 3D printing, filament diameter is very, very important to good prints, for good, accurate, and strong prints. Because if you have smaller diameter than what you tell the 3D printing slicer software, it will not be, your print will not print out at 100%. And if it's over, it will overprint over 100% of what it should be. So basically things get all out of whack and things aren't how they should be if you're not really close to that specific diameter that the 3D printer wants. In most situations it's 1.75 millimeter and 3.00 millimeter. And 75% of the time it's 1.75. And then the other quarter of the time it's 3.00. And sometimes you have 2.8 and stuff like that, but that's less often an occurrence. So the dimensional control will measure the filament size, and then what will happen is it will go over a pulley, which I'll talk about later, and then it goes into a spooler, which is basically a spool with a motor on it, which is a 3D printer spool or a spool of wire, spool of wire or a spool of filament. In this case it's a plastic spool, and what will happen is it will pull the filament or wire or whatever you want to call it onto the spooler, onto the spool, and it will pull it under tension. And the reason why you want tension is that when the filament comes out of the multi-shooter, it is still hot and still malleable for a few seconds. Now, what that means is that you could pull it to size to be perfectly sized. So if you are oversized at 1.9 or whatever, 1.9 millimeters with your target being 1.75, you could pull with the spooler, add more tension, and it will stretch the filament equally on all sides down to that specific size that you want. And that is basically taking the signal from the dimensional control at what the current size is, and if it's too big, the spooler will speed up and add more tension, and if it's too small, the spooler will slow down and release and have less tension or release tension. And now already in my head, as far as thinking about the design and what's going to be an issue, and that being said, in this video series I have not designed it yet. I'm going to be designing it in line with the series. So this video, at the point of this video, I have not designed anything. I have not touched any CAD work or anything like that. So this is all going to be live with the series. So this could change as we start the product development and we see some issues popping up that need to be changed in order to get things to be correct. Alright, blah 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 blah. Okay, so already one issue that I see is that with the spooler, with the same amount of motor RPM on the spool. As the diameter increases, or the radius increases, the tension will increase for the same motor RPM. So as a little bit of a fail-safe of that, or a little bit of a roundabout way of that, is to have something that has constant radius or diameter. So in that case, I'm going to use a pulley. So there will be a pulley right before the spooler, and that pulley will measure force on it, so that you set the tension at the pulley, not the tension at the spooler. So that way you have something that has constant radius, and the tension should never change. So if you have 1.75 perfectly and it doesn't move, that tension at that pulley will always stay the same. And then finally we have a Hall effect sensor that will measure RPM of the roller, which I'll get to in a second. That will tell you how quickly you're outputting filament to get to a certain mass. So usually in 3D printing filament, it's 1 kilogram, which is 1,000 grams, which is 2.2 pounds. So it'll tell you how long it would take extruding to get 2.2 pounds out of the machine. Alright, so more in detail of how these guys are going to work. Basically the dimensional control, this is just to give you a visual in your mind, as I'm not really that great at sketching, which I probably should be. So I mean, it's gonna obviously become very, very apparent in the CAD work. But right now, I'll give you what I see in my mind to try to communicate with you in words, which is not always the best way to communicate, but I'll try my best. So the dimensional control is going to be made up of two rollers, two cylindrical rollers that are 3D printed. All these parts are going to be 3D printed except for the motors and the sensors. So two 3D printed cylindrical rollers, and then halfway down the roller there's going to be a little crevice or a little ridge. There's going to be like a little half moon indent all the way around the roller, and that's where the filament is going to ride in. It's going to ride in that half moon little groove, the groove in the roller, to keep it from moving back and forth on the roller. So keep it in the groove. So both rollers are going to have that half moon where the filament rides in between the two rollers. The bottom roller is going to be pinned to the point where it does not move and is only constrained to rotate. So it only rotates. The top pin is constrained to rotate and move only in one axis, whether that's X, Y, Z, depends on which coordinate system you use. So it just moves up and down. And now it's almost like a suspension system, right? So depending on the filament diameter, that pin will ride up and down. And the reason why it goes back down is because it's going to ride on two springs, two metal springs. And that will cause constant pressure on the roller to keep it, tight on the filament as the filament vibrates in diameter or goes up and down in diameter. So if you could visualize one roller spinning, the top roller spinning as well as moving up and down on the filament as the filament gets pulled through by the spooler. Now, underneath the spring, the way it measures diameter is underneath the two springs is going to be an FSR, otherwise known as a force sensitive resistor. I keep saying relay. Force sensitive resistor. And that will measure force put on by the spring, and by using that force, we could determine the diameter of the filament using Hooke's law, which is basically F equals kx. K being the spring constant of that particular spring, and x being the diameter of the filament. Cut in half or whatever. Yeah, that's pretty much It depends on how I design the roller, what exactly x would be. So it'd be like x minus some constant or x plus some constant. And by using cheap FSRs, we will be only looking at relative force. So what I mean by that is, how they have the industry standards, the standardized measurements of pounds and kilograms. We don't really care how accurate this this measurement is. So if I put something on it and it says it's 2 pounds or whatever, and it's actually 3 pounds, we don't really care because we're measuring relative. So what I mean by relative is that when you get the machine, you're going to calibrate the machine where you take a piece of 1.75 millimeter wire or filament like you would get from any manufacturer, and you're going to put it in the rollers and have that set as the force that you need. So let's say it says it's 2 pounds, and let's say in actuality it's actually 4 pounds or whatever, who cares? It's just saying that 2 pounds is 1.75 for this particular sensor. So that's a little calibration piece. But what the force actually is in actuality, we don't really care. We just care that it is at what 1.75, the force of 1.75 millimeter exerting on the roller is telling that sensor it is. So let's say if it's 2 pounds for 1.75 and it says it's 4 pounds, it means it's too big, speed up the spooler. If it's 1 pound, it's too low, slow down the spooler. And that is how we're going to sense the diameter of the filament in order to modulate the speed of the motor on the spooler. Now the next piece that it goes through, the filament goes down farther, and then it goes over the pulley. So the pulley is just a simple 3D printed pulley, and that will also have the same mechanism as the roller. The pulley will have probably like a 45-degree angle with the spring and the force sensor. Now, and it's obviously in tension because it's pulling. It's basically pulling the pulley up and towards the spooler. So the pulley obviously has to be lower than the spooler. So that way, because of the pulley being there, it allows the dimensional control to go straight through the dimensional control and inside that groove, rather than move because of the spooling system. So it keeps it all on one axis, one straight line all the way down as it goes over the pulley. And also by using the pulley, we could set also another relative tension on the pulley to have so we delete any sort of change in radius on the spooler. Alright, so it continues going through, and when it goes to the next part, it is the winder, which is right before the spooler. So what the winder does is it's a servo that moves left and right to wind the filament evenly along the spool. So to utilize the whole entire spool width and depth. So by going back and forth left and right, it will utilize the whole entire spool. And then finally, there is the spool that will be attached to a geared motor, DC motor, controlled by the multi-extruder electronics system, which is an Arduino Mega, and that is running what I call the MOS operating system. So it will communicate. The Mega will communicate with a dual H bridge, L289N, that will use PWM to control the speed of the motor up to 255 resolution. That's pretty much what we're going to design. So, as far as how the series is going to go, we're going to do some CAD work and some prototyping work and some electronics work to add these functionalities in the MOS operating system and add these 2 expansion modules to get perfect size filament every time to be used on multi-extruder as well as other extruders as well. So it's going to utilize CAD and 3D printing, some electronics, some motors, some PWM stuff, and and then some manufacturing for because truth be told, I've already sold a few of these pre-ordered units, so people are already waiting for these to be developed. So some of these have already been sold. Alright, so that is it for this first video on the intro of this particular product. I mean, it could be a full-fledged product because you could add it on any extruder you want, but in this case it's just an expansion module for a multi-extruder. Alright, so looking forward to this series. Please subscribe for videos in this series, and other series like it, and I'll see you guys in the next video. Thank you guys for watching. Take it easy. Peace.